In this class, we'll see how to create rigid body simulations in Houdini. Basically, how to make objects interact with each other, be subject to forces such as gravity, fall down, and collide with other objects in the scene. In this way, you can create a large number of simulations. This course is for those who are new to Houdini. However, we don't start completely from scratch. We published another course here in the platform that covers the very basics of Houdini, such as viewport navigation, nodes, attributes, and so on. So, if you are completely new to Houdini, we recommend to take a look at that class. Now we can start having fun with rigid body simulation in Houdini. In this first section, we'll look at how to create a simple simulation like this. Basically, stones falling from above and impacting the ground. This will enable us to investigate many of the fundamental principles of rigid body simulations in Houdini. The first thing we must do is to create a new project. Let's navigate to the File menu. We'll select New Project here. We can select which folders to create. We also have to name the project and choose a path. The first step is to create the basic element that will take part to the simulation. In our case, we have a simple sphere that we'll use to make the rocks. We also have to create the main container of the objects and simulations. Move the mouse over the node panel, then press the Tab key, and type Geometry. Select the Geometry node. This is a container node, where we'll create all of the elements of our simulation. Double-click on the node. The first step is to add the basic element of our simulation, which is the sphere that represents the rock. Again, press the Tab key, type Sphere, and select Sphere Create. This enables us to create the basic element, namely the sphere. At this point, we must introduce the first fundamental concept necessary to understand how simulations work in Houdini. Making a simulation means calculating the movement and rotation of this object due to gravity or interaction with other objects. So, the position and rotation of the entire object must be calculated. If we have a plane, the object falls and then bounces like this. The issue is that, in Houdini, there is no concept of rotation or position associated with the whole object. We have a position for each individual point. Each object in Houdini, like most 3D software, is made up of a collection of points. When we move the object, we are basically moving each point that makes up the object. As a result, the movement of the whole object is obtained. If we open the geometry spreadsheet, we can see this even more clearly. We can see some informations for each individual element that makes up the object. We can open both the 3D viewport and the geometry spreadsheet at the same time. Select Split Left-Right by clicking on the arrow in the upper right corner. The viewport type here is Geometry Spreadsheet. As we discussed in the introductory course, this panel provides information on each of the elements that comprise the object. That is, the points, vertices, and primitives. Returning to the list of the points, we see a list of all the points that make up the object. We can see the three basic properties, which are the x, y, and z-axis positions. As we can see, moving the sphere's origin, we are basically changing the position of every single point on the object. As I previously stated, when performing a simulation, we have to calculate the position of the object as a whole, rather than each individual point. This allows us to assign the position and transformation of the object as a whole. Because there is no transformation associated with the object as a whole in Houdini, we must perform a preliminary step before computing the simulation. We have to convert the object into a so-called packed object. Let's return the object to its original location. Now I'm going to add the pack node. Type pack and select the node. As previously stated, this node combines the object's points into a single element. As a result, we have a single point associated with a single transformation. What happens if I connect the sphere to this pack node? As we can see, all the individual points, edges, and faces that made up the original object simply vanish. And as a result, we have a single object made up of a single point. This is also visible in the geometry spreadsheet. When I click on the sphere node, we can see all of the points that make up the sphere. However, there is only one point on the spreadsheet associated with the pack node. So, the object is now represented by a single point in space, which determines the object's position, rotation, and scale as a whole. Now I can add a transform node and link it to the pack node. We can change the position by using the handle tool. As you can see, I'm only changing the position of one point in space, rather than all of them as before. And this is exactly what Houdini needs in order to calculate the object's position throughout the simulation. Another benefit of using a pack node in simulations is that it saves memory. In fact, I'm going to add numerous copies of the sphere. If we duplicate the original sphere, we are basically making many copies of the same object. This means memorizing all of the points and elements that make up the sphere. When we create a packed object, we add a memory reference to the original object. Now, if we duplicate the packed object, Houdini creates a simple reference to the same object. To better understand, consider the following practical example. Assume we connect this transform node to the sphere. Then, I add a transform node and move it to a different location. We created two copies of the sphere, thus duplicating all of the points and other attributes. If I repeat this operation 100 times, Houdini creates 100 copies of the same object. But, if I do the same thing, by duplicating the packed object, I have only duplicated the objects in memory reference. So, the information and attributes were created in memory once, and then were added additional pointers to the same location in the computer memory. This saves a lot of memory, and makes the simulations run faster. We can now proceed to see how to create our first simulation, once we understand the concept and the importance of the pack object for simulations. We now have a packed object, which we can see by looking at the data in each node. If we move the mouse over the node and click the middle mouse button or the info icon, we can see a summary of the properties and many of the attributes of each element. Here, we can see that there are 266 points on the sphere. If we look at the object's properties, after the pack node, there is only one point left. The same thing we said before. The next thing we want to do is make a simple simulation using the object we just made. We need to add a dope network in order to do this. This is the node in Houdini that runs simulations. We can think about the dope network as a magic box. We give this box the ingredients it needs to make the simulation we want. In our case, the sphere we made is a component of this simulation. So, we need to give this ingredient to the dope network. Then we can change some of the properties of this magic box, and the simulation we want will happen. Dope network stands for dynamic operator. We need to point out something important now. Most Houdini simulations can also be created with the shelf tools. They have a set of ready-made elements that we can use to make simple simulations. We have the fluid shelf tool as an example. We can also make simulations of fire and flames. We can set it up so that rigid body simulations are made automatically. This means that we can pick an object and have the nodes we need for that simulation added automatically. The type of simulation we chose is then put into a dope network node. However, we won't use any of these pre-made simulations in our course, except in a few specific cases. We will start from scratch with everything. So, we will add all of the nodes in this dope network individually. This may seem harder at first, but it's the best way to really understand how Houdini works and how all the nodes work. Also, it's the only way to make simulations that are much more complicated and advanced than what we could make with the tools we already have. So, in these lessons, we'll learn how to set up the basic elements and add all the nodes we need from scratch. Well, this is our magic box, where the calculations for the simulation take place. But right now, it's just an empty box. Because of this, we need to add the elements we need. To do this, we need to enter the node by double-clicking on it. As you can see, it's almost empty, because we're starting from scratch. Before we move on, I want to make it easier to see the nodes, since this is the most important panel we will use throughout the course. So, I want to see both the dope network and the geometry nodes. So let's split the panel in half by clicking on this little arrow and choosing Split View Pane Top Bottom. This way, the nodes are shown in two windows. I want the nodes of the geometry, which is our sphere, to be in the top part, and the dope network at the bottom, so we can see what's inside. So, we need to lock this panel so that it always shows only the content of the geometry node. I click on this icon to do that. Good. So, even if I move inside other nodes, this view will always stay the same. We can go to the dope network in the bottom panel. I want to remind that many of the concepts I'm talking about, like node management, panel visualization, attributes, and so on, were covered in the introductory course, which you can find here on the platform. So, if you are new to Houdini, I really recommend you to start with that course. I also want to point out something else important. Here, at the top right, you can see a text that tells us what we're looking. So, at the top, we are inside the geometry node. It contains all the geometry we need in our simulation. This means we are in the context of geometry. On the other hand, here at the bottom, we are in the dope network, which stands for dynamic operator. So we are in a different context, and we can see the word dynamics here. In other words, we are in the context of the dynamic components. Now we need to put the first part of the simulation into our magic box. That is, the object we want to simulate, which is the sphere we made in this case. We can connect the output of the pack object to the first input of the dope network, so that the sphere can be sent to the dope network. These inputs are the elements we can connect. Basically, the stuff we want our simulation to take into account. Now, we need to bring the object we want to simulate into the dope network. If we press the Tab key, we can see all the nodes in this network. Really, there are a lot of them. The group of objects is the set of nodes we're interested in right now. As you can see, there are many different kinds of objects that we can import. We need the object that deals with simulations of rigid bodies, which are these. We need this object in particular, which is called RBD packed object. That is, an object related to the rigid body dynamics, and more specifically a packed object, which is exactly what we did before. Here it is. But we have to tell where to take this object from. From here, we can do that by choosing Geometry Source. Then, we can choose which input to get our object from. In our case, this is the first context. Now, we need to connect the object to the simulation's output. This makes the object show up in the viewport. Okay, that's great. We've imported the object we need and linked it to the output. But nothing happens when we press the play button. This is because we still need to add two more important parts to our simulation. The so-called solver is the first of these. The solver is basically the heart of the simulation that does all of the math and calculations. Because of this, we also have a list of these solvers in the list of nodes. There are a lot of different kinds of solvers. Here, for example, we have a solver for simulating liquids. Then we have the solver for fire and flame simulation. We also have something called the rigid body solver, which is shown here. These solvers are the simulation's engine, or brain, which do the actual work of calculating the simulation. So, we'll pick the solver we need for this particular case. I'm going to select the rigid body solver, because we are doing a rigid body simulation. Put it between the imported object and the output. As you can see, the rigid body solver has a lot of properties that we will talk about later. Right now, what we want to know is who is in charge of putting together the whole simulation. Again, though, nothing has happened yet, even though the solver is supposed to run the simulation. This is because in the simulation, we still don't have any force. It's as if we have an object in the empty space. It can't be moved by any force. For a basic simulation, we have at least to add the force of gravity. We can see a section about forces by pressing the Tab key. Here, there are a lot of forces we can add. Gravity is the one we're looking for. So I'm going to pick it and put it between the output and the rigid body. Gravity is set to its actual value, which is about 9.8. We finally have a simulation at this point. Our object falls down because of the force we just added. One useful thing we can do is turn on the real-time button so that the timeline moves in real time. And this depends on how many frames per second we set in the general properties. The object falls down when the simulation starts. But we don't want the object to fall forever. Instead, we want it to hit a plane in the floor and bounce back up. What we can do is add a base plane to the simulation. Type ground in the list of nodes and then choose the ground plane. We can do a merge between the ground plane and the force of gravity in order to join the two nodes together. The important thing is that we also need to define what kind of relationship we want, and we should generally choose mutual. This means that these two components of the merge node can affect each other no matter what order they were added in. If not, the order we put them in is important. Most of the time, the ground plane should come first, then the force of gravity. Even so, nothing happens, because the sphere is stuck in the ground plane. So I want to move the ball up so it can fall and bounce on the plane. We have to go back to the geometry node, where we made the sphere, to do this. Then, we add a transform node. And let's connect it to the sphere. The important is to connect this node after the pack node, so we will put it here. We already explained the reason for that. That is, we apply the transform node after the object has been changed into a packed object. So the change is made to the whole object, not to the individual points that make it up. If you see this error symbol, it means that we are ahead in the timeline. We need to start all over again. Remember, whenever we make a change to a simulation, we have to go back to the beginning of the timeline. If not, the simulation won't be calculated right. So we go back to the first frame. Choose the transform node, choose the hand tool, and move the sphere. At this point, the sphere falls to the floor and bounces around. Congratulations! You're done with the first simulation in Houdini. In later lessons, we'll learn how to change these parameters to make it more fun. Now, let's figure out how to make more copies of this sphere and set up the final simulation. I want a lot of balls to fall to the ground. A very convenient method of duplicating objects is to use a node that adds a single point in space. Then we'll duplicate this point and copy the sphere at the position of all these points. But let's see in practice how this works. First, I'm going to add a single point in space. To do this, I use the Add node. With this node, we can add a number of points at any place we want. If I click here, I add a point in space at this location. Now I want to replicate this point in order to create a point cloud. To do this, I'm going to use the Point Replicate node. As you can already see, we have created a point cloud. Now I can define some of the properties of these points. I can also choose the shape of this point cloud. Also, how these points must be spread out in space. You can choose from a number of geometric shapes. We can choose a box, a sphere, and other shapes. For example, we can choose a circle, placed on a plane, that we can orient as we wish. In this case, I choose the ZX plane, so that it is parallel to the ground. We can also add noise, to make these points less evenly spread out. But before we move on to the other parameters, let's look at how to make a copy of the sphere at these points. To do this, I use another node, which is extremely useful in Houdini, which is the Copy to Points node. This node copies an object to points that we have created. But remember that the object we want to duplicate, as we learned earlier, is not the original sphere, but is the packed object. This in order to optimize memory and have usable objects for our simulation. When we move the mouse over the two inputs, the tooltip appears and tells us how to use them. In the first input, we need to plug in the object to be copied. In the second, we will connect the template of points that we just made. When the visualization is turned on, the sphere is duplicated at each point. Obviously, the spheres are now very big. So, to get the distribution we want, we need to change some parameters. We can use the Point Replicate properties to do this. In the Shape section, we can choose from a number of options, such as changing the size of the point distribution. So we can increase the distance between points, and this allows us to also distance the spheres. We can also act, as I mentioned earlier, by changing the position, or by adding noise. This changes the distribution in space of the points. But let's say we want to leave the points where they are, and only change the size of the spheres. We can do this, using the transformation of the individual spheres. Let's restore the original values. Then, connect the Transform node to the Copy to Points node, and change the transformation of each individual object. For instance, we can make it smaller. We can modify it as much as we want, and get such a distribution. However, there is another method of doing this, which allows us to vary the size of the spheres in a less uniform way. By acting on the Transform node, all the spheres are the same size. So, we have to try something else. I bring back the size as it was before. At this point, we need to talk about another very important concept, the attributes of each point. If we change the attributes of this point cloud, we can also change the properties of the objects that are copied onto it.